Hello, welcome to this lesson of linear algebra. We're going to do our final problem here on finding eigenvalues. And then in the next section, we'll continue our discussion and teach you how to find those eigenvectors. This will be a special matrix that I'll use because I want to show you that you can use everything in your power to find these darn eigenvalues. What if you have a large matrix, 5, -2, 6, -1, 0, 3, -8, 0, 0, 0, 5, 4, 0, 0, 0, 1. We want to find the eigenvalues of that matrix. First thing you do, which is the thing you always do, is you find the determinant of this matrix that's modified as follows. 5 minus lambda, -2, 6, -1, 0, 3 minus lambda, -8, 0, 0, 0, 5 minus lambda, 4, 0, 0, 0, 1 minus lambda. So you take the diagonal elements, you subtract lambda, everything else remains the same, and you're setting this determinant equal to 0. So you have to decide for yourself how to find the determinant. If you want to expand about this row, then you're going to have a little tough time because at every step of the way, you'll have a determinant of a 3 by 3 matrix left over, which, as you know, is quite a bit of work anyway. And since the determinant has lambdas everywhere, it's a lot of algebra to keep track of. In this case, we notice that the matrix we were given is already in triangular form. And remember, you can find determinants if you can get the matrix in triangular form, if it's already like that in this case, or if you do your own row operations to get there. Then basically the determinant is the product of the diagonal elements. So because this one's already triangular, you already know that the determinant is as follows. 5 minus lambda, 3 minus lambda, 5 minus lambda, 1 minus lambda. You know that that's the case. So in this case, it's already falling out because it's triangular, but even if there was, like, let's say a 1 here or just a 2 here, let's say it was pretty close to triangular but not quite triangular, then you would just do quick row operations to get it triangular, and then you have your diagonal elements. It's much, much easier than expanding, doing a cofactor expansion, if your matrix is already triangular or very, very close to being triangular. Now we have a double benefit here because this is the determinant here. Now we can do all this expansion and collecting terms, but that's silly because all we really want to do is figure out what lambda is. Because of the way it's structured, all of the terms are already in the right form to write down directly the answer. This one means that lambda is going to be equal to 5 because I'll set this equal to 0, make a -5, divide by -1. This one means lambda is equal to 3. This one means lambda is equal to 5. And this one means lambda is equal to 1. So I didn't even have to expand it. So it's worth your time, I guess is what I'm trying to say, to look at a problem, especially a test problem, and just make sure that you're attacking it the right way before you jump into cofactor expansion or something and go crazy. I have to say, though, even if you did decide to do cofactor expansion, you would never want to expand about the first row because you have all these terms. I would want to expand about the third row because then I'd have 0, 0, 0, and I would just have this one term to deal with. Or I expand about the first column because it's mostly zeros. And as you know, when you do cofactor expansion, if you have a lot of zeros in the row or the column, it basically makes it a much, much simpler calculation. In this case, we do it this way. Okay? Now notice that lambda is equal to 5. The way you would write it down is multiplicity of 2. Lambda is 3, lambda is 1. That happens sometimes with polynomials. Sometimes you get a multiplicity. That's okay. These are the unique eigenvalues. It's just you have a multiplicity of 2 on this one, and that'll come into play whenever we have the eigenvectors that we find. I'll show you what I mean by that later, but this is what you would circle on your test. You have 3 distinct eigenvalues with a multiplicity of 2. Because it's a 4 by 4 matrix, we expect to get 4 eigenvalues, and the multiplicity of 2 counts for 2. And here's a third one, here's the fourth one, and that's basically how you do it. So we spent quite a bit of time calculating eigenvalues, and I wanted you to get comfortable with it because I didn't want you to stress out about that while I'm trying to teach you the eigenvectors. So what we're going to do now is go in the next section. We're going to talk about eigenvectors, but what really you have to do is you always have to find the eigenvalues before you can find the eigenvectors. So we'll be using that as a starting point to find these eigenvectors in the next section.